All right then, so we're finally at a position where we can tackle a numerical example here. So this is what we're going to work on in this video. We have an element here which represents just some position, some point within a structure. And it just so happens that the stresses that are acting on that element are represented here. Now, one of the ways we might have obtained these stresses would be that we could have a real structure with a series of strain gauges bonded to that structure. And by using Hooke's law, we can work out the corresponding stresses. So we don't need to go too much into the detail on exactly how, or well, we're not going to go too much into the detail on exactly how one obtains this state of stress. We're just going to work on the assumption that we could have obtained somehow the stresses within an element, within a structure at a given point, and those stresses are represented on this element. So what have we got then? We have a horizontal stress, compressive stress of 32.5 newtons per millimeter squared, so that corresponds to sigma x. Sigma y corresponds to 82, or rather 8.2 I should say, 8.2 newtons per millimeter squared in tension, and then the shear stress is indicated as a negative 10 newtons per millimeter squared. And so if we focus here on the positive x face, we can see that it's a positive face, but the arrow is pointing in the negative y direction, and based on our shear convention, plus and a minus gives us a minus. And so that's why when I see this negative arrow here, I know that that means that that shear arrow must go down on that face, must act downwards on that face, because it's the shear on the x face in the y direction, and that direction sets up the directions of all of these other shears, because our little element here must be in a state of equilibrium. All right then, so that's the setup. What do we need to find out? Well, first of all, I want to work out, I'm just picking an arbitrary angle out of the air here of 35 degrees, and I want to work out, I use my transformation equations to work out what are the stresses at that exact same point in the structure, but just on a different set of planes, right? On a different set of orientations, orientated at 35 degrees or rather clockwise. Second, we're going to work out what are the principal planes, the orientation of the principal planes. Then we'll get the principal stresses. Then we'll work at the orientation of the maximum positive and negative shear stress, the magnitude of that maximum shear stress, and then the normal stresses that are coexisting on those planes of maximum shear stress. Right, so let's just get straight into this then. So the first thing I need to do is I need to plug in theta equal to, now we said 35 degrees clockwise. Now clockwise will correspond to a negative 35 degrees, right? So when it comes to our rotations, and the reason that we assume clockwise is negative is that when we go and start looking at our Mohr circle, we want the rotation, or the sense of rotation of the Mohr circle, to match the sense of rotation of our element. Now that will make probably no sense to you right now, but it'll make sense to you at the end of the next video. At this point, we're going to assume clockwise rotations are negative and anti-clockwise rotations are positive. Okay, so we defined, or we prescribed, a clockwise rotation here, which means we're going to plug in a negative 35 into our transformation equation. And then the rest of the values we sub in are sigma x equal to a minus 32.5, sigma y equal to an 8.2, and tau xy equal to a minus 10. Now, when we plug those, I'm not going to do it out longhand, but basically you can plug that into our transformation equation 1, right, which is going to give me sigma x1, and it's going to give me sigma x1 equal to a minus 9.7 newtons per millimeter squared. I'm then going to sub into my third transformation equation, TE3, and that would give me sigma y1. And sigma y1 was equal to a negative 14.6 newtons per millimeter squared. And then when I sub into my last transformation equation, which happened to be the second one we derived, that's going to give me the shear stress on that inclined plane of, let me see, what is it? It's going to be a negative 22.5 newtons per millimeter squared. Okay, so the first thing I want to do is I want to make sure the sum of the normal stresses is constant. So if I was to take my 32.5, my negative 32.5, and I add 8.2 to it, we would get sigma x. I mean, I know this works out to be correct. I'm just sort of confirming it because it reaffirms something we said previously. So sigma x plus sigma y should equal sigma x1 plus sigma y1, because we know the sum of those two things is constant. So that would give me that boils down to a negative 24.3. And then on the right hand side, we'd have, and sure enough, that's equal to a minus 24.3. Right, so we're off to a great start. So all that really tells us is that we haven't made a mistake in executing our transformation equations, or certainly the ones for normal stress. So the next thing to do is visualize that, right? So we've calculated some numbers. Let's visualize. Well, first of all, we have our element rotated a negative or a clockwise 35 degrees. So let's draw or sketch that guy out. So it's going to be something like this. Okay, so that's my 35 degrees clockwise. And now we can just draw our stresses on. So we said sigma x1 was a negative 9.7. Negative means that it is a compressive stress. So I'm going to draw it as such. Now, the fact that I'm drawing an arrow here, the arrow is capturing the fact that it's compressive. So I won't bother drawing on a negative or writing it as a negative. I'll just say 9.7 because the arrow tells me it's negative. We do the same on the far side, so that's going to be 9.7 also. Now, what else did we say? We said sigma y was minus 14.6. So again, that's a compressive stress, sigma y1. And then the shear stress on the x1, y1 face. So that's this face here, right? The shear stress on that face happens to be negative. Now, that is a positive face. It's the positive x1 face. The shear stress is negative, which means the arrow must be pointing in the negative y direction. Okay, because if it's a positive face, the arrow has to be in a negative direction. So that means that shear stress is going to go that way. So that's going to give me a shear stress of 22.5. And again, I leave off the minus because the arrow is already capturing the sign of it. And of course, that sets up the direction of all of my other shear stresses as well. All right, so there you have it. In a nutshell, we have employed the transformation equations to just pick an arbitrary angle, 35 degrees, and determine the corresponding stresses. Okay, so the next thing we want to do is go on and work out the principal planes. So let me jump over here now, and I'll calculate my principal planes. So for this, we'd worked out the equation tan of 2 theta p is equal to 2 times the tau xy over sigma x minus sigma y. So that's going to give me 2 times a minus 10 over minus 32.5 minus 8.2. That gives me, take the tan inverse or the atan or arctan of both sides, gives me 2 theta p equal to 26.17, and then theta p, one of the values of theta p is equal to, we won't say whether it's theta p1 or theta p2 yet, we'll just say one of them is going to be 13.08 degrees and the other one, theta p, is going to be 13.08 plus 90. Remember, these principal stresses occur on mutually perpendicular planes. So that's going to be a 103.08. Okay, so I've got two planes. I've got two principal planes here, and I know my principal stresses develop on these planes, right? So we could independently work out what our two principal stresses are, but to determine which stress develops on which at which angle, the easiest thing to do is to take each of these different angles and sub them into our transformation equations. So when we sub in theta p equal to 13.08 degrees, we sub that into a transformation equation. What are we going to get? We're going to get a principal stress equal to a negative 34.8 newtons per millimeter squared. Excellent. And we do the other one. We'll say theta p is equal to 103.08 degrees. When we sub that into a transformation equation, we're going to get 10.5 newtons per millimeter squared. Now, the algebraically largest stress is going to be the major principal stress, and then the algebraically smaller one is going to be the minor principal stress. So major and minor principal stress. So it turns out sigma 1 is going to be 10.5 newtons per millimeter squared, and that's going to have a corresponding angle theta p1 equal to 103 degrees. So another name for that is the major principal stress, and then sigma 2 is going to be the other guy, obviously, and another name for that would be the minor principal stress. Let's sketch those guys out. I'm going to rotate my element, my x face, by 13 degrees here. So that's it's a positive 13 degrees, which makes it a counterclockwise 13 degrees. The stress that develops on the face that's orientated at 13 degrees is a negative 34.8, right? So that means a negative means it's a compressive stress. So we know we know that we have a 34.8 newtons per millimeter there, and we're going to call that sigma 2. So sigma 2 is equal to 34.8, and of course that means we have sigma 2 equal to 34.8 on the far side as well. And then the stress that develops on the face that's got its outward pointing normal orientated at 103 degrees would be this face here. Now that has a stress of 105, or rather 10.5 I should say. So 10.5, that's a positive 10.5, which means it's going to be a tensile stress. And that arrow should be perpendicular to that face. My sketch isn't amazing. So that's going to be 10.5, and that's going to be 10.5. Excellent. And of course we know there are no stresses develop on these principal planes. So that is all of the stresses that are happening or occurring, and it's probably worth just drawing in our angle here of 13 degrees. So that one's 13 degrees, which obviously makes this one here my 103. Excellent. All right, now we can move straight on and work out the planes of positive or maximum positive and negative shear stress. All right, so we know the maximum positive shear stress occurs on a plane. We've seen this previously. Theta x1 is equal to whatever theta p1 was minus 45 degrees. So plugging the numbers in, theta s1 is equal to 103 minus 45. Theta S1 is equal to 58 degrees. Easy enough. And then the maximum negative shear stress, theta S2, is equal to theta P1, again it's P1, it's not P2, theta P1 plus 45 degrees, which is going to be my 103 plus 45, which is equal to 148 degrees. All right, and we can determine tau max is pretty straightforward. That's just equal to, remember we said it was sigma 1 minus sigma 2 over 2. So we get 22.65 newtons per millimeter squared. And again, we'd like to know what is the normal stress that exists on those planes as well. And we said that was just equal to the average value of stress, which was any sigma x added to its corresponding sigma y over 2. And so we could plug in any values there, and we'd always get the same answer, minus 12.15, as in with any pair of normal stresses on mutually perpendicular planes, and we get minus 12.15 newtons per millimeter squared. So a compressive stress. Right, let's just sketch that out. It's important that you, once you arrive at these sets of numbers, straight away you move to do a quick sketch, right? So this is going to have a face, theta S1, orientated at 58 degrees. So if I sketch that, it's going to look something like this. So we said that the stress on that face was 22.65 degrees, the maximum positive stress, and that's a positive face. So to get a positive shear stress, we must have the arrow pointing in the positive y1 direction, which is going to be this direction here. All right, which we now know that sets up all of my other shear stress arrows. And we can draw on the normal stresses as well. We said the normal stress was a compressive 12.15, and that's going to be the same on all sides. So this is 12.15, and the shear stress we said was 22.65. All right, so we've used our equations to basically work out all of the stresses we were asked to work out. We know a lot about this. We know a lot about the state of stress at this particular single point within our structure. Okay, remember, I've drawn all these different states of stress, right? So we started off with this one, right? So that's the first state of stress. Then we worked out the corresponding state of stress at the same location in the structure, just on a set of planes orientated at a 35-degree angle. So that was our second stress state. Then we worked out the principal stresses, right? So that was the third stress state. And then we worked out what the maximum shear stresses were. So that was our fourth stress state. The key point here to recognize is that the stress at that location in the structure is not changing. We're just viewing it at different angles or different orientations, or in other words, we're viewing the stresses that develop on planes at different orientations within the structure at that very specific single point. And remember my vector analogy. The underlying vector, the vector is analogous to the stress state here. The underlying vector isn't changing, but the components, the orthogonal components that can be used to describe that vector, they're changing depending on how we want to, along what set of axes we want to resolve our vector. It's the very same idea here. The underlying state of stress isn't changing. We're just seeing different magnitudes of the components of stress depending on what orientation or what orientation we want to look at our stresses developing at. All right then, so I think what would be a good exercise now is to take this, jump over to our notebook, implement this really quickly in code, and then plot our transformation equations, and then plot some of these key values onto those equations, just so just to really bring it all together.